Hi, if you're watching this, I'm recording my lab on my iPad instead of screen recording it because I'm having issues, but I gotta turn in this lab on time, so bear with me here, I'm sorry. Lab 2, projectile motion. So, the purpose of this lab was to model the projectile motion of an object with resistance, and this being drag. And the fundamental principle for this lab was the momentum principle, which describes a change in velocity under a constant net force. And a brief summary of the results found that the model version with drag was more similar to the observed data than the model that did not incorporate drag. So the main concepts and models for this lab was, as I said, the momentum principle, which is final velocity equals initial velocity plus F net divided by mass or acceleration times time. And this describes the change in the velocity of a projectile, specifically in the y direction because it undergoes a constant net force. F net explains how drag contributes to the change in velocity because F net counteracts Fg, which is F net itself, which will therefore be less than Fg, but I'll get to that. Because the first model assumed there was no drag, the second model assumed drag was squarely proportional to the speed of the object, also known as turbulent drag. And the observed experiment itself was with an object with high surface area, so there was an assumption that drag was present. For the experimental design, the system was an eraser, and the surroundings were the earth and surrounding air. The initial conditions were the eraser was 2.75 centimeters in width. It was dropped from 1 meter, and it had a mass of 0.0091 kilograms. This movement exists only in the y direction, and eraser was chosen due to having a high surface area. Therefore, it would be more prone to decelerate due to drag, or F net would be lower significantly than F of G, versus like dropping just like a rock, which really does not have that much drag undergoing it. And then for coding, Model 1 just had the grav arrow position as 0, 0, 0, and the grav arrow axis as 0, negative 9.8 acceleration due to gravity, and 0. And then Model 2 had identical for the gravity, but the drag arrow in the y direction was the ball's velocity squared. This was also in the opposite direction due to gravity to show that the forces work against each other. The results show that the observed data was most similar with a computer that incorporated drag compared to the one with no drag. But the similarity they have is that the change in position, sure, it's getting more negative, but it grew exponentially in a sense, and that's because the velocity is increasing constantly, increasing linearly due to a constant net force. Now, this net force with the observed in computer with drag is, drag plus gravity, and so that's why the computer with no drag was not very similar. But the general trend of the graphs are similar because they both have a constant net force, thus updating the velocity, thus causing the object to gain more distance quicker. Um, so again, since Model 1 didn't incorporate drag, it differed from the observed, and the Model 2 was more appropriate because it mimics real-life conditions. They all had a more negative decrease in velocity, but the speed was increasing. And then a possible error was that the eraser was kind of wobbling a little bit, and so the surface area wasn't constant, so drag wasn't hitting, perpendicularly, I guess, exactly as often as it was when it was flat, which can cause it to, not fall as fast. And then, so for what does it mean? Which model demonstrates terminal velocity? And that would be Model 2, because for the first model, F of G is going to be the only force acting, and thus the velocity is going to be constantly increasing, or I guess decreasing, but it's going to get larger or more negative, has a greater magnitude, aka the speed. And the terminal velocity for the second model, because the speed will get so fast, it'll eventually counteract F of G, and F of G will equal F drag, meaning net force is 0, so velocity is constant when net force is 0. If it were thrown with some initial speed that were somehow to overcome terminal velocity, the force of drag would be greater than F of G, and the object would slow down until it reaches terminal velocity, and thus it would stay at terminal velocity. This would also be the same terminal velocity no matter what. So no matter how fast you throw it initially, drag will eventually overcome and then equal F of G, and thus the object will continue to fall constantly.